By the way, I wrote some things on the whiteboard.
Sorry?
I wrote some things on the whiteboard. I might take it over. It's small. I can take it.
Yeah,
I wrote some things there.
maybe you want to bring it closer because I can't see because I'm an old man, huh?
No, I mean I would bring it when the video starts.
Yes.
Um,
Okay, maybe you want to explain to me. Yeah, I see. Let's see if I get it. So yeah, I see. The force on the left is again, I is
it's
your
the quark formalism and the mass formalism.
yeah, right. So the one on the left is the more general one and universal, and on the right one is the more to relate to what we understand of, you know, in the
Yeah, and this is how you calculate the G values.
right. Yes, I see. I see. I
And
see.
it's gravitational acceleration. But practically, you can just look at the ratio between your G value of the element with the G value of iron, and you multiply that with the free fall acceleration of iron. Because because obviously you cannot every location has a different small g, right?
So why do you always base all your work on the iron? Why iron specifically? Is that a
Maybe you want to start recording before you ask too many questions.
no, it is already recording, I think.
Oh,
It is,
it's recording? I didn't click OK. I have to click OK, then it's recording.
oh, can you click?
So I will click OK in a moment. Okay, let me click OK. And I send you a request as well.
Can you again then explain it? Can you bring it again? Can you just
Yeah, sure.
repeat such that we have it on board? So can you
Okay,
repeat it again?
so
Can you repeat what you just said then?
this is the Newton's gravitational force formula, but in the quantum gravity version of it. This
Yeah,
is number of quarks in the first object, number of quarks in the second object. This is the chromogravity constant. It's about 10 to the power of minus 65 or so. And the units, it's like the same units as in the gravitational constant, but multiplied by kilogram to the square.
okay.
Um, divided by the square of the distance, and this is the mass formulation here.
Yeah,
So here you have the geometric mean of the gravitational constant of the big mass and the gravitational constant of the small mass.
yeah,
And here you have the big mass and the small mass.
right.
And so when you equate it with the force formula M times G or M times A,
Yeah,
that's then the M moves over here and is canceled, but it's still left here. It's still the a trace of it is still left. The G value of it is still in part of the formula. But practically speaking, small g is always different in every location, so it's not so meaningful to write down small g values for different chemical elements. What you do is you just look at the ratio between um, the g value of the material you're using and the g value of iron. And why iron? Well, it has the biggest free fall acceleration.
I see.
You're really only interested in the ratio between different chemical elements. Like, I mean, if you were you can also just calculate the time difference that you expect there for different chemical elements. And here's the is how you calculate the G value of hydrogen. Is you have to calculate out the binding energy. So
Yeah,
this is the mass of iron atom, and this is small because
yeah,
it's reduced by the binding energy. So this is the small number, and this is the big number. It's the number of protons times the mass of proton, number of neutrons times the mass of neutron in iron,
I see.
and so this is big, this is small, so this makes this smaller, and so that you get the much smaller gravitational constant of hydrogen, and then you can use that as a basis of calculating the gravitational constant of any other element. So here you have an element X, so you have the number of protons in element X. number of neutrons in element X and the mass of the element X.
Right,
So
right.
that's how it's done.
So and so going back to your first formulation, which is the more
Yeah.
universal. Yeah, this G, how do you estimate it from data? Is it estimated from data like experiments, recent experiments, or
Yeah, from data you basically take the gravitational constant of the hydrogen
okay,
or the proton, yeah, the constant of the proton, and you multiply with the average of the mass of the proton and the neutron, and then you have basically the gravity per quark.
I see.
So you have them kind of hidden inside. You have the mass hidden inside. So it's so you don't need to multiply it with the mass anymore. That's
Okay,
why it's used together with a natural number, not a mass. So this is without units. So
yeah,
that's why I like to use the set theory formulation of using the blackboard letters.
yeah, right, right, right. I see, I see, I see. Uh-huh. So then, my next question is, um, one of the big difficulties with the current models that we have. Again, I'm not an expert in gravity and so on. My field of research is completely different, but I have a keen interest.
You feel this? You're a mathematical neuroscientist?
Yeah, exactly, exactly.
Mhm.
And so I come more from the field of dynamical systems, geometry, topology, and I'm applying these
Mhm.
ideas to understand certain aspects of the brain. But in particular, one of the key works that we work on is epilepsy, Alzheimer's disease. For instance, our research group, is discovering that, I mean, we have a strong hypothesis now that Alzheimer's, in fact, is an infectious disease. Whereas the traditional viewpoint for now 116 years was that it was based on a protein misfolding of a protein. But now, with new findings, we are, like, for instance, if you take um, uh, all people that have died of Alzheimer's disease, you take their brain, the frozen brain, and then you do a PCR test on these amyloid plaques, you find basically pathogens. And so now hypothesis has led to this infection hypothesis of Alzheimer's
Mhm.
disease. So now we're trying to see how we can develop drugs in this direction. So we
I
have an
see. Does it? Yeah. And my view on memory is that the same as Sheldrake's, namely that it doesn't truly reside in the brain, but it's accessing all the information is stored in the non-local realm, um, also called the Akashic records.
yes,
And
I've
so
heard
the
of it.
brain would be more like a receiver.
Yeah, I've heard of it. Yes, I've heard of it, but these, so I have nothing against it. The point is that when we do science, and as you do science, you need to have a way to relate to what you observe and measure, right? And so this is more difficult to relate to. So I wouldn't have a way to.
Yeah, there would still be there's still neural connections, but they're more like small notes. Like I met this person there, and all the details. Like you can remember all the details, like every tree, every leaf. You might be able to remember, or you might think, okay, I'm just imagining to be able to remember all of this, but actually we remember. I believe that we remember much more than is encoded in the brain. I don't think that you can take a brain and read out all the memories.
Yeah, I mean, it's true that the basis of memory has not yet been fully understood in neuroscience. We don't really know. I mean, this is the honest assessment. All the experiments to date has not managed to categorically show what is the neural basis of memory. So who knows?
So for me, remembering is basically remote viewing.
Yeah,
Yeah.
yeah. Well, yeah. My mom believes
It's
that.
just easier because you have traces of it in your brain. You have some notes, small notes. I call them notes, and that's why it's easier to do remote viewing on yourself than on other people.
Yeah, maybe. Again, these are very open questions. But so what we try to do in my case is like I don't look at these questions because these are questions that are almost impossible to answer from a scientific perspective. That is, what kind of measurements do I do in the lab to justify this? It's very hard.
Well, it's only impossible because people are ideologically opposed.
Yeah, but the
I mean,
point.
Sheldrake does plenty of experiments, and they very much follow the scientific method. Dean Radin has done very many experiments, and his p-value is very high. It's 1 in 10 to the power of 15.
So what kind of
Uh,
experiments has he done?
one,
What kind of experiments has he done?
like for example, you can look at a random number generator and look how
Ah,
if
yes,
you
yeah,
wish to have more ones than zeros, you get more
yeah,
ones than zeros.
yeah,
And
yeah,
the meta-analysis, this 1 in 10 to the power of 15,
yeah.
and in individual studies, 1 in the to the in 10 to the power of 12.
Yes, yeah, no, yes, I recall this. And there's
But
also
he didn't receive a Nobel Prize for it.
Princeton University, in fact, has run interesting experiments called the
Although the threshold is 10 to the power of 6.
yeah, I think yeah, you're right. Yes. Princeton is running some interesting experiments called the Global Consciousness Project. And it's all in this
Yeah, I've talked with Roger Nelson a few years ago, and he follows my research sometimes a little bit.
interesting. Anyway, I need to buy your book for sure. I'm gonna buy your book and see if I understand, and then we can
Thanks.
end.
Yeah, that's the book. It arrived here. I ordered it, and that's a maximal number of pages, 780 pages. And if you use the normal format for the book, it would be 1,500 pages because thin A4 is not a normal format.
Oh,
And I
okay.
guess you cannot easily walk around with such a big book.
Yeah, yeah,
Yeah,
for sure.
I'm just reading here.
No, it's fascinating what you're doing. I have four questions. One question that I do have is that, as you know very well, the current models that we have can't explain, for instance, the effects of gravity or accelerations that we see or what we observe in the galaxy, like very in the far distance. All these models, like Newton's model, Einstein's, for long distance, basically they fail. Okay.
Well,
It's
they don't really fail. It's just that people believe in this ridiculous Big Bang model where the universe is ridiculously young. It's like when I read it, it's like I'm talking to some creationist who thinks the Earth is 3,000 years old. That's what modern cosmology is for me. Um, if you calculate the age of average white dwarf, actually 65% of them are older than the mainstream age of the universe. And that's using some simple thermodynamics, like anyone could do it. Um, but I guess they make up a conspiracy for every second star. They make up a conspiracy why it is younger than it looks.
well, how do
They
you
would say,
calculate?
okay, it collided with something,
Yeah.
and that's why it lost some mass, and that's why the apparent age is not the true age. But they could do that a few years ago. Like they could do that maybe 30 years ago when they could not see the very faint white dwarfs, and but now we see so many white dwarfs that every second white dwarf is already a anomaly. So you hear the word anomaly all day in astrophysics nowadays.
Yeah.
And that's not normal. You cannot have anomalies all day and then still clinch on until this old theory, which in my view has been disproven already 5 years after it was established, because think Zwicky proposed dark matter in 1930 or something. And that's just disproving the model, because it's not dark matter, it's just burnt out stars, which you cannot have if the universe is very young. You cannot have so many burnt out stars and stellar black holes. But nobody ever frames it like that. They always say, oh, there's this mysterious dark matter. But no, it's just burnt out stars, and you cannot account for them because your universe is too young.
So these burnt out stars, well, typically is you again. I want to understand fully because your viewpoint. So normally, when a star explodes, and under certain conditions, it collapses under itself, and then it may create a black hole, correct? So what you're saying about,
Yeah, 1 in 1,000.
yeah, but what you're saying is different. It's not the same concept, right? It's not black hole formation. It's just burnt
No,
out.
it can be just burned out stars. Most of it is just burned out stars. Doesn't need to be black holes.
Mm-hmm.
It's
Mm-hmm.
still dark if it's small and it's burned. I mean, I have found 16 black dwarfs, which shouldn't exist. If you Google black dwarfs, it says don't exist, cannot exist. But there are plenty of them. Like
What do you
there are
mean?
many papers with an
Ah,
invisible companion, which should be in the mass range of a white dwarf.
what do you mean you found? You found, like, you found papers.
Found online. Like there are many papers which
Uh-huh.
are overlooked, where people have found double star systems where
Yeah.
one companion is invisible and the right mass for being a white dwarf,
Mm.
but it's invisible, but it's a distance where it should be visible. And for it to be invisible, it has to be incredibly cold. And usually when they discover such a star, they assume in the paper, they assume, oh, we have to assume that it has the maximal possible temperature while still being invisible, because if we don't assume that, we get into big trouble with Big Bang Theory. And so that's what every single paper is saying. But even if they use the maximal possible temperature, it's still gonna be older than the universe. The problem is just doesn't seem so extreme anymore. But it could be zero. The temperature could be just zero. And I calculated actually there's a way to find out the probable temperature of them. And I did the calculation was quite complicated. It needed some higher level math. And basically, I even found some white dwarfs that had a temperature below zero. One of them was below zero, I think. Yeah.
It's in your book as well, these calculations.
Yeah, yeah, it
Okay.
is.
The cosmological, okay. That's intriguing. That's
The
intriguing.
formula had some power of 3 and power of 2 in it. So I had to, if you use the exact solution, you don't get exact answer, but you can find the exact answer, but just trying out the different values. So it took me 5 hours to do this for 14 white dwarfs. But I also wrote down the exact solution because it looks more elegant when you have some
Yeah,
exact solution. But
yeah.
it's not exact. Sorry, the algebraic solution is not an exact solution. Yeah.
So what is the age of the universe then in
Yeah,
your
42 trillion years. 42 trillion years.
40, what?
Yeah, 42 trillion years. It's a number 10 to the power of 13, 4.2 to the power of 13 plus minus 1. And that's based on the Hubble constant, which is, or the Hubble parameter, which is measured using supernovae, not the CMB, because that's too theory dependent, too model dependent,
Yeah.
and wrong actually. Yeah, but that's the post-decoupling age of the universe. That's the age of the universe after the universe became transparent.
So so okay, so first of all, you don't believe in Big Bang. Do I get this correct? So you don't believe in.
Yeah, the maximal density, the maximal temperature in my theory is 6,000 Kelvin. So that's not very hot. It's not Big Bang like.
Yeah, right. And so, okay, so what is your postulate or hypothesis of how the universe initiated? So we know that there is this quantum sub-zero energy,
Yeah,
and how does
the
it?
universe, sorry, the universe expands in order to compensate for the entropy increase in supermassive black holes. So it's fun to compare the laws of thermodynamics and the laws of cosmology, according to me. So the laws of thermodynamics, the first law says that energy is conserved, but the first law of cosmology is saying that the energy is always reduced because as the universe expands, actually not drops in density. As the universe drops in density, the photons in the cosmic microwave background are losing energy, and so the energy is not conserved, and people already know that, and even Robert Chadwick has pointed that out, that the laws of thermodynamics are a bit weird in cosmology. So in before 1997, it was still possible to say the universe is a closed universe, which when you move forward all the time, then one day you will arrive at the same position. It's like a hypersphere. And in such a universe, you could say, okay, this lost energy is returned to the universe later when it's collapsing, because this kind of universe slows down and then collapses, but our universe is accelerating, it's not collapsing. And so the energy is not conserved. And it's accelerating because when you feed a black hole linearly, like one, for example, one donut per second or per minute, then the surface area is growing like a quadratic function because surface area is always square. So and that's why entropy is also growing quadratically when the entropy when the mass is growing linearly, which
Mm,
it does.
mm.
Um,
And
and
this by data, right? So always appealing to data, right? This is
Yeah, it's always by data and very a huge amount of data.
yeah.
Like I tested the distance because if you claim an age of the universe, you also claim a distance to the CMB, distance to any remote galaxy. But that's only important after 200 million light years. Then that's when expansion really kicks in
Mhm, mhm,
because nearby, the local movements of galaxies are bigger than what the expansion is causing in them, and so you cannot observe the expansion locally.
mhm, mhm,
The Earth is not expanding, for example. The solar system is not expanding.
mhm,
So that's not just because it's gravitationally bound. It's really would be too small at this scale.
mhm. So
So I looked at the if the luminosity of supernova is decreasing with the square of the distance, and it's not doing that in Einstein's theory in mainstream cosmology, but it does so in my theory. And people have already found that the remote supernovae are too faint, and they try to solve this problem by proposing that the expansion of the universe is accelerating, and so that kind of made the problem more mild, but it still existed. They're still too faint,
mhm,
and if you use my theory, then it's not too faint. So this analysis of the maybe I have it here. Yeah, it's here. So in the book, I normally superimpose the two graphs here. I made this transparent and superimpose it. So
yeah,
this is um, luminosity. Luminosity decreases here normally, but here this is magnitude. So magnitude is an inverse square measure of luminosity, and so quite counterintuitively, is it increases with the distance.
yeah.
Actually, it means that it's becoming less bright, but because it's an inverse logarithmic measure, that's why it goes up. So unfortunately, it's so counterintuitive, but anyway, so it goes up here, and you see that for Einstein's theory, you measure it to go over this line here, the first square here, but here it goes on the second. So here it arrives at the second
Yeah,
compartment here,
yeah.
but here it's the first. But here you can see that it fits perfectly. The data match for my theory, the data matches perfectly, but here it doesn't match at all. So this is what you see in when you read articles about cosmology. You always see, oh, we have a galaxy with a record redshift, and it's at 13 billion light years. Oh, we have a new record, and you see like double the redshift. See, like going from redshift 7 to redshift 12, and the redshift 7 was already like 12.9 billion, and redshift 12 is like 13. So all the redshifts are basically at the same distance. It's
Mm,
ridiculous. And I heard of another researcher. this name I learned about him just 2 days ago. One of my viewers recommended him. I can't remember the name right now, but he was doing an analysis uh, on the size of the galaxies as you see them on the apparent size, and the true size, and he found that all the galaxies are too small for the distance in the mainstream model. So the mainstream model is wrong to a degree that is it's laughable. Like and when they look at the two faint supernovae and they try to solve this problem, the only solution they can come up with now is things like, oh, maybe the physics of supernovae are changing over time. Maybe the constants are changing, and that's why everything doesn't make sense. Those are very desperate solutions.
Okay.
Any solution where you just adjust some number randomly, it's always a desperate solution,
Right.
including all the Mond theories,
Yeah.
modified gravity. Those are random. They're not predictions.
Okay, so let me understand. Then okay, so this is cool. But for you, what triggered the origin of the universe then? Just to understand
Yeah.
from your theory, what would
Okay, so something that you need, like you don't need dark matter, but what you need is you need something that is kind of similar to dark matter because you need to explain how galaxies formed. Like if you just have primordial soup with sorry, and not hot primordial soup, like 6,000 Kelvin, it's hard to have galaxies form in them. So my theory is deriving quantum mechanics from more fundamental principles, and so I have these elementary spaces which are complex valued. So the surface area is a complex number, and so complex number are very important there. So so every mass is actually a complex mass, and the imaginary component, if that flips to negative, then that's an antiparticle.
Mhm.
And if the real number flips to negative, then that's exotic matter. But it's exotic matter that still has positive gravity. So because you see that gravity always depends on these absolute values of sets, so that's always going to be a positive number. So
Mhm.
gravity is always positive, even if mass becomes negative. So I believe that there were primordial black holes, and it's very mainstream actually to believe that there are primordial black holes, because that's basically the only way you can explain galaxy formation. And the problem is much bigger for mainstream cosmology than for my theory, because in my theory, there are 42 trillion years time, and in the mainstream, they have no time at all, and they need to explain how galaxies formed almost in an instance. Well, that theory doesn't make any sense anyway, because they have huge galaxies already right after decoupling.
Yeah.
So
So then
yeah, but
when I go back then to the question, so what causes black hole formation then?
yeah, so the galactic supermassive black holes were caused by primordial black holes, and those are basically exotic holes, like exotic matter black holes.
Mm.
Um, their gravity is more similar to electrogravity than to chromogravity, so it's weaker and smaller distance, shorter distance, but it's enough for having seedlings, have seeds for black holes, for supermassive black holes. But as of an origin story, it's not like an origin story. It's not like in the mainstream Big Bang theory where you have a matter antimatter war. Basically, you have matter antimatter annihilation, which was generated from just pure light. That doesn't make sense in my book because, I mean, they are saying that you had like 1 million particles, antiparticles, and 1 million and one particles. That
Mhm.
never happens in any experiment on Earth. So
Mhm.
maybe they can imagine when you have such high temperatures that the laws of physics, the symmetries don't apply, but that's pure speculation. And I'm not doing that speculation because it's a very hand wavy thing to do because you're basically saying, oh, I don't know why there would be matter left, but oh, let's just put that for as a question for the future. And so then they can get research funding forever because nobody has a clue how it's supposed to work, but they say, oh, maybe there's a way to find it out. It's very similar with string theory. They have no way of determining the shape of the extra dimension, but they say, oh, maybe one day in 50 years there will be some way in which the shape of the extra dimension is not random, and so then string theory will be a theory that makes predictions. As for now, it never was a theory.
Yeah. Right, right. I see. Very, very fascinating. Really fascinating. Okay.
Thanks.
So then I have yet another question. Then going back to your formulations in the blackboard and so on, how do you explain light? Light. How does light emerge? Light. I mean, in your theory, in the context of your theory, how does photons emerge?
Okay, so every mass is a complex mass, and yeah, so fermions would be elementary space quanta that have 2 dimensions, and bosons have 1 dimension, and that makes sense because you when you look at the spin, for example, of a photon, it has lost 1 degree of freedom. It's not like the electron, which can point in any direction. It has to be in the direction of the propagation of the light.
Mhm.
And there you can have spin up and down, but not in different directions. Yeah. So it has a chirality,
Mhm.
but it has less degrees of freedom than the spin of an electron, let's say.
Right. Yeah. Right. Mhm.
And the symmetry groups of the standard model, you can get them from the properties of elementary spaces. So U1 corresponds to the one-dimensional elementary spaces, which is really two-dimensional because it's complex numbers. And SU2, you can get it from the fermionic elementary spaces. And SU3, you can get it from having the overlapping elementary spaces forming this seemingly three-dimensional space. It's not really three-dimensional, it's two-dimensional, but they are overlapping. And so if you have some flower of life pattern here, but with random radii for the circles, you can only move on the surface of the circles, and the more circles you add, the closer your dimensionality comes to 2.
Mhm.
But so you have 1 divided by n, the number of connections, and but for 3 dimensions, you want to write down 1 divided by square n, because you need much more connections to get a feeling of three-dimensionality than
Right.
you need. Like for two-dimensional, 10 might be enough to get a feeling of, oh, I'm feeling like I can already move freely in 2 dimensions. But for 3 dimensions, 10 wouldn't be enough. You need like at least 100 or more to feel like you're moving in 3D space.
Yeah. Okay. So yeah, I get it. So then I go to yet another question because really want to understand the core. So you do believe in this idea that real vacuum does not exist. You have a quantum field, and experiments.
Yeah, the quantum vacuum. Yeah.
Yeah, exactly. And experiments show that if you shine, for instance, a photon on this vacuum, matter emerge, like atoms emerge. In your theory, this is still supported, right? So this is
Well,
perfectly.
there are particles and antiparticles, but there's no net generation of matter. It's not possible to generate new matter. And that's why Hawking radiation is so wrong. In Hawking radiation, you have the baryon number conservation is out the window. The lepton number conservation is out the window. I mean, the only reason that people don't care about that is because they already assume at the Big Bang, light created more matter than antimatter, and that already violates baryon number conservation. So they don't seem to care about the laws of nature that much. So baryon number conservation is violated, lepton number conservation is violated, and then also the second law of thermodynamics is violated. And there are, so because you have the big black hole has a huge amount of entropy, and when that is turned into light, pure light, that's not a high entropy.
But
So now people
why
like to claim,
why do you rely so much on on this idea of conservation, given that in an expanding universe you don't need this, and in fact matter is emerging from this quantum.
Because a black hole is a closed, can be analyzed as a closed system. You can put a box around it and treat it as a closed system.
Yes and no, right? Um,
Of course, strictly speaking, every system is open, but you
right.
still have the law of thermodynamics, and then you have the law of cosmology. Because you have the law of cosmology doesn't mean that local laws of conservation aren't violated. If you have photons and they don't traverse cosmological distances, you're still expecting the conservation of energy to apply.
Yeah, I see
You
it.
only don't expect to apply when you reach cosmological distances.
But
Okay,
but, but
so
at the beginning, the photon does traverse the whole cosmological distance, right? You know, in
yeah,
a
yeah. So you have the laws of cosmology there. The conservation of energy doesn't apply, but I'm not talking about other things. I'm talking about lepton number conservation, baryon number conservation, and that's not affected at all. In
right.
cosmology, it still applies.
Hmm. Hmm. Hmm.
So then you have the second law of thermodynamics. People claim that it's not violated by Hawking radiation by saying, oh, well, the radiation goes into random directions, and this introduced randomness increases the entropy. Well, it does not really increase the entropy because the entropy is updated. When you make a measurement, you're reducing the entropy by knowing where every particle is. So in a black hole, it's like a black box. You don't know what the configuration of particles is inside the black hole, and that's why it has a huge entropy. And when a black hole is evaporating in the Hawking theory, then you can go and measure every single particle, reducing the entropy tremendously, getting rid of all the entropy basically. And not everyone swallows that the second law of thermodynamics is not violated by Hawking radiation. Roger Penrose, for example, in his book says he supports Hawking radiation because it's crucial for his cosmological model of CCC. But he has quite hand wavy arguments. He says after the evaporation, the entropy of the universe needs to be recalibrated or redefined. So he's basically admitting that there's a huge problem there with the second law of thermodynamics.
Right, right, right. Okay, I think I got pretty. I don't want to take much of your time because otherwise I'm abusing your time. I I'll, I'll I'll want to meet you again and discuss. But for now, I'll read your book. I definitely want to read
Mm.
it. It's quite astonishing what you're doing, I have to say.
Thank
Uh,
you.
it's quite unique. I will read, try to understand, and go into depth, and then hopefully at some point I will want to reconvene with you and discuss further
Mm.
because then I will have more more insights from.
Yeah.
I
Mm.
just have a final question before I leave, um, which is, going back to the completely different scale now, going back to the bucket experiment, where you got these
Mm.
um, uh, the bucket experiment by Newton. All these ideas of centripetal force, Coriolis force, for you, this is still valid within your framework, correct?
Yeah, well, I guess you want to ask if the bucket would still bulge when not the when the earth, when it's not the Earth rotating, but
Yeah, yeah,
the universe rotating.
yeah,
Not let's put it that way. The Earth is flattened out by its rotation. So I
yeah.
guess the question you have is, what if the Earth was standing still and the universe would be revolving around it?
Which is, yeah.
Would it still be flattened out? I guess so, yes. But but for me, Mach's principle is about asking why there seems to be an absolute